Okay, exponential functions and their graphs is a topic today. An exponential function is a function in which the variable is an exponent. X is your exponent. So f of x equals a to the x is an example of the general form, the parent function, of our exponential function, where a is going to be greater than 0. It's kind of nice if it's not equal to 1, because 1 to any power is going to be itself, right? So that would be kind of a pointless case. So examples include f of x equals 3 to the x, f of x equals 1/2 to the x, f of x equals 0.8 to the x. A is always positive, and x is our power. This is what it looks like graphed. For some general number a to the x, we're always going to go through the point 0, 1, because anything to the 0 power, when x is 0, anything to the 0 power is 1. So your exponents will always go through here unless we do some shifting. Exponential functions. And then will be 1 over and a up, no matter what, because anytime you take some number to the first power, you always get that number. Yep. It doesn't matter what number you take to the 0 power, it's always going to be 1. So 5 to the 0 is 1, 17 to the 0 is 1, 23 to the 0 is 1. You're always going to get 1 no matter what when you take it to the 0 power. Always going to be a 0.01. Unless we shift it, and we'll talk about the parent shifting. Okay. Absolutely. Everybody got the graph jotted down, sketched out? Okay. What's the domain of this function? All reals. We can be anything, right, for as far as x is concerned. So negative infinity to infinity are all real numbers. How about the range? Good. 0 to positive infinity. This looks like it's asymptotic to the x-axis, right? We'll never, ever, ever touch 0, so we'll have a open bracket or open parentheses, 0, comma, infinity. But if we shade our y's, all of this is what y can be, up and down. To write it in the non-bracket form, you're going to say all real number such that y is bigger than 0. Can't be equal to. Okay. Where is it increasing? When x goes from negative infinity to positive infinity, right? It's always increasing. Really, it's a range, yeah. So that's probably the only way that we can write it is the interval notation. The interval on which it's increasing is everywhere. Okay? Is it decreasing? No. What's the y-intercept? When x is 0, sorry, where are we crossing the y-axis? When x is 0, y is 1. Okay, so far so good? Here is f of x equals a to the negative x. So this is the point negative 1a. We have the point 0, 1. Our function is called a to the negative x. That's the domain. All reals, we can be anything, right? What's the range? Yep, anything greater than 0. Where is it increasing? It's not. Where is it decreasing? Negative infinity to positive infinity. What's the y-intercept? 0, 1 again. Because a to the negative 0 is still a to the 0 going to be 1. Okay? Anything to the 0 power is 1. Yes. Good question. And the answer is yes, if we do some shifts to it. Yep. We have to add something to it to make it shifted down. And that would have to be a negative k, right? To be able to shift it down however many steps. Yes. Good. That's the next logical thought, right? So let me see if my link will work. How would we graph this? Okay, so let's pick on one. We'll pick an easy one. Okay, so here we go. So now we are going to do a graph of one. This is supposed to be, sorry, it's small, y equals 2 to the x. So we picked a number a. A happens to be 2. We can't use 1 because it's not even worth talking about. We're going to put 2 in there. Okay, 2 is an easy number. So we'll start plugging in some values for x and see what happens. Okay, let's do the easy one. We said that anything to the 0 power is 1. So when we plug in 0, we're going to get a 1. Okay. And must not be zoomed quite right. Okay. Now let's put in 1. 2 to the first power is going to be 2. Okay. We'll put in 2. 2 to the second power is going to be 4. We put in 3. 2 to the third power. 2 times 2 is 4, times 2 is 8. Easy to do. Okay. Now let's think about those negative numbers. 2 to the negative 1 power. What does that mean to do? Flip it, put it in the denominator. A negative exponent means to switch it. If it was in the numerator, it now goes to the denominator. So if 2 is now in the denominator, what is 2 to the negative 1? 1/2. So this is going to be 0.5. And 2 to the negative 2, a fourth. So that's going to be 0.25. Okay. Everybody see that? So we've plotted 5 points, 6 points. Now let's look at the graph and see how it looks. Going to keep shooting up really high on the right-hand side, and it's going to get very, 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 very close to the x-axis, but never cross it, never touch it. Okay? Plugging in values for x, seeing what that exponent does to our base. Okay? All right. All right, so families of graphs. Okay? It's not bad. This is easy. We learned about this back in chapter 1. Remembered it, hopefully, from algebra 2. And we have an a times an x minus h plus k for our function, no matter what that parent function is. A, we always talked about that, how much it stretches it. If it's a number larger than 1, it would stretch it really, really tall. If it's a fraction, it's going to flatten it, right? It's like it's having less slope. We're rising less and running more. Whereas if it's a value bigger than 1, we're rising a lot and running very little. It's also called the amplitude. We'll especially talk about that when we talk about sinusoidal functions. Then we have h. H is our horizontal movement. How much is it moving to the side, left or right? Okay. And then k is our vertical movement. Notice I put a k in vertical. I misspelled it intentionally to help you remember that that's your movement up and down. Okay. So we'll remember and refresh our memory on how this worked with parabolas. There's our good old x squared, right? Vertex at 0, 0. When we're one step away, 1 squared is 1. So we're one step up. If we're 2 steps to the right of our vertex, we're 4 steps up because 2 squared is 4, right? And we have a line of symmetry, so -1, 1, and -2, 4 will also be points on that graph. What happens when we subtract 3 within the parentheses? Goes to the right 3. Very good. Okay. What happens if we take 5 away from the x squared? Goes down 5, so it's shifting it down 5. Okay. What happens if we take 3 times the x squared? We introduce an a. Stretch. Is it going to make it flatter or fatter or taller? Taller. Okay, because we're rising 3, we're taking 3 times that 1, 1 to get up to 3 or 1, 3. Okay. So what do you think is going to happen with 2 to the x? If I take away 3 from x, the exponent itself, what's going to happen? Everybody agree? What's going to happen if I take away 3 from the x? Up here you told me it moved it right 3. So let's check and see. Does it move it right 3? Absolutely. Okay. So instead of the point 0, 1, we're now over here at 3, 1. We moved it 3 steps away. Okay. 0, 1 translated over to 3. 1. Okay? Very cool with that? What do you think is going to happen when we take that 2 to the x and subtract 5 from it? It's going to go down 5. So let's find out. Ta-da. Okay? So instead of 0, 1, this is going to be 0, negative 4. It was 1, going down 5. Okay? Everybody cool with that? Okay, here we go. Last one. What's going to happen if we take the negative of x? It's going to reflect it, right? Which way? Across the x-axis? Across the y-axis? Across the y-axis. Okay? Because remember, we're dealing with fractions here, right? If it was 1/2, x to the 1/2, or 2 to the 1/2, it's now going to be 2 to the second. So it's going to reflect it across the y-axis. 0, 1 will still be there. But when we were at 1, 2, this will be negative 1, 2. When we were at 2, 4, it will be negative 2, 4. Okay? We cool with that? All right. Okay. Euler's number. This is important in calculus limits. It's important in exponential decay, like radioactive decay. Important in banking, interest and things like that. Euler's number is the letter E, occurs in nature, and it is an irrational number. Remind me, what's an irrational number? The most common irrational number that most people remember is pi. What's special about pi? Never ending. Never terminates, never repeats. Euler's number, E, does not terminate, does not repeat. Also known as Napier's constant and the natural base. So with pi, we say it's 3.14159 6, and so forth. E is approximately 2.718281. And it's the base in the natural log, which we'll talk about tomorrow. So the natural log is also known as the log base E, and it's about equal to the log base 2.718. Log base 10, yep. On your calculator is log base 10. Okay. Everybody done writing? All right, next slide. So let's talk about compound interest. Compound interest is what makes your $200,000 house cost $600,000 over the course of your loan. You end up paying for your house 3 times over. if you pay all 30 years. Also, why investments make a huge difference if you are saving for retirement. Well, you want to start when you're in your 20s and not your 30s or 40s. Compound interest allows you to make money on the money that you've made money on. Okay? You don't just start out with $2,000 and you put it in. You actually make money on the $2,000 plus the interest, and then interest on that $2,000 plus interest plus more interest over time. Okay, so we're going to talk about compounding interest n times per year. The formula for that is A equals P times the quantity 1 plus R over N all to the NT power. A is the amount you're earning, your final amount. It's your final answer. P is how much you invested initially. It's your principal. How much you've invested or how much you've loaned. N is the number of times the interest is calculated in a year. Do they do it monthly? Do they do it quarterly? Do they pay you interest yearly? What do you think R stands for? The rate as a decimal. 5% interest rate, 0.05. 7.5% interest, 0.075. Okay? T is time. Okay, yes. It is the amount invested or loaned. Okay. So have you seen this formula as well? PERT, okay. So again, amount that we're making or loaning over time after it's all said and done. P is your principal again, how much you loaned or invested. R is your rate. T is the time of the loan or the time of the investment. Same as the others, yep. Okay. But notice that it's got this letter E here, and E is Euler's number. Okay. The one that we just talked about, Euler's number or Napier's constant, the natural base, 2.718. Okay, PERT. All right, so you've loaned the bank, you gave money to the bank, put it in the bank, and they're giving you 6% interest rate. That's not likely right now. Okay, you're very lucky to be able to make 6% on your money for 10 years. Find out how much you would have in the bank if it's compounded monthly versus continuously. So remind me, what was the monthly? Yep. Write it every time. Practice it so you remember it. Okay. Continuously, you said was PERT. Okay. So here we go. Our amount that we're going to get is 10,000 times 1 plus my rate, 6%. Number of times monthly. How many times do they do it a year? 12. To the 12 times what? 10 years. Okay, so we're looking at 10,000 times 1 plus 0.06 over 12. What is that? Calculator? 0.005. Okay, so 0.005 and to the 1/20th. Okay, so 1 plus 0.005 is 1.005. Have to take that to the 120th power first before I can take it times the 10,000. We're talking money, right? So let's do 2. Okay. So 1.005 to the 1/20th. And I'm taking that times 10,000. So thanks to compounding interest, $18,193.97. That's how much the bank is going to give you. Two decimal places since we're dealing with money. It would be, it's always better to keep it, don't do any rounding till the very bitter end. Okay? Everybody knows how to run their calculator, knows how to do these? Okay. So now let's talk about PERT. Yes, thank you. It didn't look right when I wrote it up there. All right, so amount, again, $10,000 principal times e to the 6%, right, times 10 years. So 0.06 times 10. Okay. Now you know how to run that in your calculator as well, right? We want first e to the power. So where's your e button on your calculator? Yeah, it doesn't show up very well up there. EE is not it. That's your under exponent. It should be under ln on yours, yes. Get a different calculator here. Okay, so we're going to take e to the 0.6. It's above the ln, so second ln. Yep, 0.6, because it was 10 years times 0.06 for our rate, so 0.6. And we're going to take that times 10,000. So here we make $18,221.19. Which one's better? Continuous. Okay, it's compounding every hour, every day, every second of the day type of thing. Whereas the other one is only once a month. So the bank, when they charge you interest, they're going to charge you based on continuous. When they pay you interest, they're going to pay you based on monthly. That's how they calculate it. Okay? problem similar to this on your CSA, your midterm. Coming up later. Got to get through chapter 3. Population growth. Okay, we have growth of population. We have a city increasing according to the model P of T equals 32,000 times e to the 0.0367 t, where t equals 0 represents 1980. Graph the model and use it to predict the population in 2008. Plug in numbers. So anything to the 0 power is going to be 1, right? So in 1980, we're at 32,000. Okay, everybody cool with that? So at 0, we're at 32,000. There's 20, there's 40, halfway between and a little bit up. There's our base population at that time. Okay? Then we want to plug in other numbers. I wouldn't plug in 1, I'd plug in 10, right? We know that we're going to be somewhere, we're looking at 2008. How long after 2000? Well, we're not, yeah, 28 years. So we're probably going to want to plug in for sure 10 and 20, and then also 28. Because they want us to graph it, to sketch the graph of the model. And then eventually they want us to actually tell what it will be in 2008. Okay? So this is just a whole bunch of problems where we say 32,000 times e to the 0.0367 times 10. Figure out what that is. That'll be your 10 comma something. And then 32,000. Yep, find out where it's going to go. Because they want us to not just, they want us, the answer, or they asked us to graph the model first. And then once we have it graphed, figure out what it's going to be in 2008. It's just a number. You can choose 5 or 7 or 13. So 32,000 times e to the 0.0367 times 20. 32,000 times e to the 0.0367 times 28, which is 28 years after what they were looking for. That would be what it should be in 2008, provided everything was consistent. Okay? So do you ever wonder where these equations come from? Yes? Do they just pick them and pull them out of a hat? Just randomly generate? All right. So here's your assignment. And if you're curious about where these kinds of things come from, you have the power on your desk to come up with these kinds of equations. If you have access to the internet and Desmos, you have the ability to come up with these kinds of equations. Okay, this $110 or $98, depending on whether you got it on sale, that gives you the power to predict things. And if you want to get 5 points bonus on your test, it doesn't have to be today to turn in tomorrow. Okay, I have a sheet that has some examples of some data that you can use to come up with an equation just like this. It has all the steps for your TI calculator or for Desmos to come up with an equation for how much wind energy we're going to be generating over the next few years. It's not hard. It's actually really kind of cool. Okay? So as soon as everybody gets this written up, I did not get your test graded. Nope. At least 5. We'll see on the last test. Yep. I didn't have a bonus question on there, so I wanted to give you a chance to get some bonus points. But I promised that I would teach you how to use your graphing calculators, so this is one of my steps. Let's say by Monday. Mm-hmm. Thank you. Where am I at? Yep. Okay. Uh-huh. I'm going to try to get them graded today during 4th hour is my plan. Okay, so let me show you kind of where we're going here. Uh-huh. Give me 1 second. Why is it not working? Uh-huh. Mm-hmm. Mm-hmm. Okay, so the graph that I gave you is kind of hard to see on your paper. This comes from my website. So if you go to sistree.com and you search for Nebraska in there, you're going to see a picture that I took from my dad's house. This is actually of one of our neighbors. But you see the windmills in the background? It's becoming pretty common. We start to see more wind generation in Nebraska because we're kind of a windy state. So if you go to the Nebraska Department of Energy, they have a graph and tables of data that tell you how many kilowatt hours, billion kilowatt hours of energy we have been generating over time. We started out doing this in 1998 when the first turbines were kind of put in. And as you can see, it looks like we're growing, right? What kind of a curve does this look like? Exponential, which is what we were just talking about, right? And so if you get that data, which is what I gave you on your sheet, there's a table on to the right side. I put them all in since 2001 is where we're starting because I have data for how much energy we use in Nebraska as of 2002. Okay. The crazy thing is, even though we're going up, the yellow is our wind energy. The orange is petroleum. Coal is the purple. Natural gas is the blue. And we have a little bit of hydroelectric. It's red down here. You can barely see it. Okay. If you like this and enjoy it and want to do more extra credit, I have data as well on the total energy consumption. And you can find out when we could potentially, if we keep growing at the rate that we're growing now, when we could potentially be completely free of fossil fuels for power generation. 10. Okay. The test is I don't know. Yeah, I haven't graded it yet. Okay.